This is Sheikh Mirkatul Hakim. Today I'm going to do a presentation on general concept of electromagnetic interference shielding, in short, EMI shielding. The presentation will cover its background, some theories related to its parameter, and also we will learn about some shielding materials. EMI is a general term used for electrical signals that interfere with the normal operation of electronic equipment. All electric and electronic systems and equipment generate some kind of signal that may potentially interfere with the normal operation of another nearby piece of equipment. Also, EMI can degrade the performance of electronics, introduce errors or operational faults, or cause complete failures. It may be self-generated, where one circuit interferes with another, or externally produced by some other device or equipment within the same environment. The definition of EMI shielding is the practice of reducing the electromagnetic field in a space by blocking the field with barriers made of conductive or magnetic materials. A conductive enclosure is used to block electrostatic fields, which is also known as Faraday cage. There are various types of EMI can be found in surrounding depending on the sources. Narrowband EMI, which typically emanates from intended transmissions such as radio, TV, or mobile phone. On the other hand, broadband EMI is an unintentional radiation from sources, for example, electric power transmission lines. Any kinds of noise, either external or internal, is also a form of EMI. Man-made noise coming from sources like fluorescent lights or auto ignitions is the worst type of external noise. Spikes on the AC line caused by switching loads such as motors, contactors, or relays off and on are instances. There are some potential sources of EMI. People intentionally or unintentionally are responsible for the sources, mainly coming from electronic devices or other electrical power sources. Besides, natural phenomena associated with Earth's magnetic flux, lightning can also cause the outcome of EMI. The necessity of EMI shielding comes from daily basis. Without shielding, electronics would not function as designed or may even stop working altogether. Highly sensitive biomedical devices like pacemakers or other life support devices may have bad impact for the patients who uses them. Anthropogenic electromagnetic noise also affects biological processes, including human health. The smaller size and the faster operating speeds of these components make it more challenging to manage EM pollution. The EMI shielding can prevent access to data stored or on RFID chips or embedded in other devices. It can be used in combination with aircraft systems to increase and complement existing security measures, such as those used in military, government, and financial systems. There are different kinds of material involved in EMI shielding. Conducting metals may provide superior performance over other types of materials. Aluminum, copper, nickel, steel sheets are traditionally used in form of gasket. They are also formed into shape that fit electronic housing or enclosures. Nowadays, they are less likely to be used for their high coercivity, processing cost, and mechanical flexibility. With advancement of modern technology, devices require cost-effective, lightweight, non-corrosive materials such as carbon matrix, polymeric matrix, and also ceramic matrix composites. These composites also provide tunable features depending on their application. There are three mechanisms we are going to talk about in respect to composite materials. The primary mechanism of EMI shielding is usually reflection. For reflection of the radiation by the shield must have mobile charge carrier, for example, electron or holes, which interact with the electromagnetic fields in the radiation. As a result, the shield tends to be electrically conducting, although a high conductivity is not required. Mainly, when the shielding material is metallic, they possess free electron to contribute in reflection mechanism. In this case, the EM wave reflects back from the surface of the materials. A secondary mechanism of EMI shielding is usually absorption. This happens when the wave is absorbed by the materials. For significant absorption of the radiation by the shield should have electric and magnetic dipoles, which interact with the electromagnetic field in the radiation. Another shielding mechanism is called multiple reflections, which refer to the reflection at various surfaces or interfaces in the shield. This mechanism requires the presence of large surface area or interfacial area in the shield. Now we will go further in depth to understand how the parameters of EMI shielding controls the physics of the mechanism. EMI is a wave having frequency over wide range, as we learned before. So definitely it will propagate through a medium, maybe vacuum, or through any materials. When you consider shielding, it most likely refers to materials' capacity to block the EMI wave. Those materials might have two inherent properties such as permittivity, permeability, or conductivity, and other properties. Some equations have been shown and derived from several references based on theoretical and experimental aspects. These equations basically show how they relate to EMI shielding and how they play synergistic roles in overall shielding mechanism. These parameters represent the properties of the media through which the electromagnetic waves propagate. We are going to discuss some of the important parameters. First, permittivity. A permittivity is simply a ratio of electric displacement field to an applied electric field. It is a measure of electric polarizability or ability of polarization of a dielectric. The polarization means the process of separating opposite charges within an object. The positive charge becomes separated from the negative charge. The process always involves the use of a charged object to induce electron movement or electron rearrangement. More generally, as a thermodynamic function of state, it can depend on the frequency, magnitude, direction of the applied field. In electrostatics, the permittivity plays an important role in determining the capacitance of a capacitor. From the concept of permittivity, we can easily understand the dielectric constant. It is as same as relative permittivity, which is actually the ratio of absolute permittivity and vacuum permittivity. In another term, it is also the ratio of the capacitance of a capacitor using the materials as a dielectric, compared with a similar capacitor that has vacuum as its dielectric. This can provide electric and magnetic dipoles, which is more important in absorption mechanism. On the other side, loss tangent is a dielectric loss which qualifies a dielectric material's inherent dissipation of electromagnetic energy, let's say heat. It is the ratio of imaginary and real permittivity. It can better describe the material conductivity. The material with loss tangent greater than 1 exhibits as a good conductor, and loss tangent less than 2 exhibits as a weak conductor. The dielectric constant and loss tangent act as a function of permittivity, which can vary by a range of frequency, where frequency is a function of EMI as well. So when this comes down to conductor, it is quite unlikely to ignore material's conductivity. Though it is not a scientific criterion for shielding, but it's really important. Conductivity is material's ability to conduct an electrical current. We need conductivity to improve conduction path within the materials, and shielding can be enhanced by conductivity. It is also called percolation in case of composite materials containing a conductive filler. Conductive filler can be carbon black, carbon nanotube, or various nanoparticles. If we consider any polymer composites, filler loading can increase the EMI shielding by enhancing conductivity or reducing the resistivity. Shielding can be manipulated by some other intrinsic or extrinsic parameters as well. The equation also provides some symbols for those. Shielding material thickness is an extrinsic parameter which can be used to control absorptions or multiple reflection dominated shielding. Here we'll learn something called skin effect, which is one of the important factors that can actually process properties of materials. The EM radiation at high frequencies penetrates only near surface region of an electrical conductor. Electrical field of plane wave penetrating a conductor drops exponentially with increasing depth into the conductor. Skin depth is considered to explain the effect. It is the depth at which the intensity of the radiation inside the materials falls to 37% of its original value at the surface. It depends on conductivity, wave frequency, permittivity. Skin depth may vary according to different materials with the change of frequency, which implies how far into a material the EM wave can go. The higher the conductivity, the lesser the insulate. The intensity of current or free electron on surface top is high enough to bounce the wave back to the direction. And the EM wave can penetrate easily when there is less electron or no free electron. Basically, this happens when we use any shielding materials which is not enough conducting. Let's say only polymer or any plastic materials. And these are my references that I use for the videos. And thank you all who watched this video, and stay healthy.